This screencast will cover the topics covered in Chapter 1. And for the future, you will find that I will have a screencast for every one of the chapters of the textbook, which also goes under the category of class notes. The textbooks or class notes for this particular class is a book that I wrote for McGraw-Hill several years ago. We never actually did get it to print, but rather than not utilizing this information, I have been using it in this class now for several years and saving all of you some dollars in terms of textbook costs. It'll be more or less our roadmap to getting through this class, as each chapter will cover a section of material that I talked about in the starting up video. And the first one here is the most basic introductory stuff, where we start talking about creating logic to satisfy a programming problem or opportunity. So, a little bit about the class, again in review of what I covered already, but just a short version this time. Please review the syllabus. The book is free, not to worry about that. You'll have 4 quizzes, 2 tests. The quizzes you can take multiple times. The highest or last score that you have will be the one that will be used. And then you'll have 2 midterm and a final, which are short answer tests, which you'll have to either, maybe put some code snippets or put a paragraph about a code snippet that's out there. And I guess for lack of a better term, these tend to be more essay or critical thinking type questions. There are 10 assignments. There are 4 discussion questions, and you have 5 reflection assignments, where each week you're going to tell me what you've learned and where you still have some questions. As far as getting help, email is the best source over the summer. I will not be in my office for much of this class. I will be on the road for part of it, so where I'm relying on email, video, Hangout, which is the video conferencing option available with Google Mail, which you all have access to communicate with students either on a one-by-one basis or as a group. Okay. Class resources. Canvas is the primary one. In Canvas, you'll have these videos, you'll have the textbook, you'll have examples, assignments, etc. You'll find that I may put some resources on the EGC system, which is our network, if you will, on the S drive in the courses folder under CIS150AB. You can, if you're on campus, copy from that, or you can also FTP from it, file transfer protocol. And I think I'll assume everybody's had some exposure to FTP, but if necessary, I can also have a video done to show how that works. Most of the time when this is done in a traditional format, students typically have thumb drives to store their assignments and ebook and all the other stuff on PowerPoints, because it just seems to be nice to be able to take to work wherever you're working on this particular class. Software, we'll use Notepad++ primarily. I will probably be using either Wing 101 or perhaps Thony, which is a Python interpreter for some of the examples where I need to show you how logic how the program moves through the logic step by step, and to test out some of the solutions that we've come up with in Pseudocode for logic. Now, as far as the PowerPoints go, obviously I'm going to be talking about them during the video, but they'll also be in the files section of the Canvas site. Again, this class is covered in thirds. Structured programming, first third. Object-oriented programs, the middle third. And then the last third is kind of a combination of things, but it's primarily event-driven processing or exception processing. And that's very, very popular with some of the newer programming implementations where we have GUIs or graphical user interfaces, and also very popular on things like PCs and mobile devices and tablets and iPads and stuff like that. What I'll try to do is mix up a little bit of these examples. So some of them are going to be tablets, some are going to be PCs, some of them might be web. I've taught in all those different environments. Over the years, I've taught Java, ASP.NET, VB, VB Advanced, Oracle, Python, Visio, CIS150. I pretty much taught them all. I've been a faculty member at GCC for about 16 years. I was at 1 year at Mesa. I'm currently the department chair, so I do mostly management activities, but I still have several courses I teach each semester. This being one of them. I also teach JavaScript and Python currently. I miss Java dearly, but that's somebody else's now. And if anybody has any questions about a class or another class or a pathway of classes, just let me know. I've been at GCC for a number of years. My industry experience, I started off as a programmer at the city of Binghamton in upstate New York. Went to Savin, General Electric, AGS, which was a subsidiary of 9X as a consultant, contractor. I worked at IBM, General Electric. I worked at Karsten Manufacturing here in Phoenix, and also was the IT manager at VSP of Arizona before coming to the Maricopa Community College system. I've been at GCC for 16 years, and I was at Mesa for 1. I also teach at NAU. Objectives for Chapter 1. The current text that you guys are using is undergoing a little bit of change, not anything dramatic. I'm trying to incorporate maybe a little bit more of some of the newer tablet technologies and cell phones and wearable devices or Internet of Things. So you might find there might be a little bit of change between what's covered in the textbook and these slides, but it'll be minimal. The beginning of each chapter talks about the objectives. One of the basic things this first chapter deals with is looking at logic as the blood and guts of a program and understanding that computers are different than people. That's kind of obvious, I guess, but they're not as smart. They can't reason. They can't learn. So as a result, creating application software or operating system software is a very labor-intensive activity. If I asked you guys to go make me a peanut butter sandwich, you could do it fairly quickly. But if I had to give you all of the necessary steps for a computer robot to do it, we'd be talking thousands, if not hundreds of thousands of lines of code just to make a peanut butter jelly sandwich from my kitchen. So this can be a very complicated topic. It can take a lot of time to create because basically computers are not as smart as us. And whereas we take things for granted and can easily reason through things and understand what hot and cold, right and left and up and down is and what looks good, what looks bad, everything a computer does, it has to be told. And if it's told wrong, it'll do it wrong. So we're going to introduce in this class a number of standards and techniques starting in Chapter 1 that will hopefully help you better understand how a computer needs to see things and how you can be a more successful programmer by creating logic that's free of any kind of bugs. Okay? The relationship between logic and a program and programming statements is illustrated in this slide here. Basically, a logic model is typically either pseudocode, which is just English-like statements, like a recipe in a cookbook, or possibly graphically with a flowchart where it's using specific symbols. Both pseudocode and flowchart will be heavily discussed in chapters 1 and 2. Okay? In fact, assignment-wise also. From this logic model, we can then begin to create the statements necessary for that computer application to execute. It may execute as a compiled application, as an interpreted application, or as a runtime application. There'll be more about that later in this chapter. But there is a relationship between. We typically start with logic, and from logic we then can build the program. In fact, one could say that this class is mostly focused on logic, so that the logic we create could be used by any programmer out there in any language they want to program in, because this logic is so fundamental to how programs or computers operate that one size, logic-wise, fits all. Pseudocode is where most of our logic will be documented with. Now, we will use Python to prove out the pseudocode. It's one thing to create a model, but it's a whole other to actually have it work. And the Python is a programming language that allows us to let it work. This is pseudocode here, and essentially what it is it's like a recipe, or it's like instructions you would get from Google to drive across town, stepwise or step by step, top to bottom, left to right, explaining a series of sequence steps. All pseudocode programs have start, and they have the word end. Start, the first part of the logic, and end indicating the end of the logic. Anything else, it's fine. Anything goes. Pseudocode is unstructured. It does not have any rules. It's basically just there to have you describe what's happening. This one's got a little bit of twist and turn on it to make it look more like a program. In other words, the first 4 statements start with a hashtag, which is the comment symbol for Python. A comment is programming documentation, which is used to add a little more explanation to what the code is doing. This is really important for someone who's going to look at your program later which invariably will happen, or if you were to go back to it later and try to figure out what your original logic was supposed to do. It's just documentation. In this case, this pseudocode is going to start here. It's going to input, it's going to ask for input with a prompt. Enter name will appear on the screen, and then using the keyboard, it'll capture the name, Gary. The next statement is a comment saying that I want it to go to the screen. And simply in pseudocode, if I want to display something or show something on the screen, I can say display name, show name, put on the screen name, anywhere I want to describe it so it's obvious to the reader that I want this information to be stored to the screen. Now, there's a little twist in here that is different for you. This information that I'm capturing from the keyboard is stored into something called a variable called name. And a variable is just a mnemonic. It's just a place to store something. It's like a nickname. It's just something that's going to hold in memory for us temporarily some value, in this case a name. So when I store it in that mnemonic or variable, I can use that throughout my logic. So below here, when I say display name, whatever was keyed in up here will now appear on my screen. That is how pseudocode acts like a programming language. But again, I couldn't run this in a computer now. I could only show it to you as text. It's like a little story. It's like a recipe. One of the things that happens, and I've already explained this, is that programming logic can be enormously complicated because of the simplicity that the computer operates under. A computer is a binary machine. It understands 1 and 0, shiny, not shiny, in the case of a CD-ROM, positive or negative charge in the case of a hard drive, and everything is just in this binary numbering system. So it's a very simple thing. So it has to be told things very simply. And what I have in this particular example is some program logic that was created in pseudocode, and as you can get a flavor from it, it is fairly simple. And then also I'm showing next to it what it would look like as a formatted language statement in Python, which the computer could run. And a lot of this is to show the relationship between pseudocode and a programming language. In other words, pseudocode is very non-structured, anything goes. A programming language has a lot of rules to make sure that the right information is executed by the computer. Now, as far as the peanut butter sandwich example, think of this. What happens if you were going to create the software necessary for a robot to build a computer, or to build a peanut butter sandwich in your kitchen? What might the steps, the recipe, the pseudocode look like to do that? Well, it might go something like this. Begin program. Go to refrigerator. Of course, it doesn't know what refrigerator is, so you'd have to have some code that says go north, go south, go east, go west. Once it got to the refrigerator, you'd have to have code that says, okay, does this pull from left to right, right to left? Is it 2 doors next to each other? Okay. If it opens a refrigerator, then it has to know what shelf to look on. So it'd have to start at the top shelf. Some refrigerators might have 3 shelves. Some might have 4 shelves. Some might have 2 shelves. Now, I have to go through it one by one. What if there's 2 things of peanut butter instead of 1? Well, then hold on, because I don't keep the peanut butter in my refrigerator in my house. In my house, it's in the pantry. So already this thing's gotten very complicated. Even to find the jar of peanut butter inside the refrigerator is complicated. We haven't got to the point yet where we have to open the jar, get the peanut butter out, find the bread, do all the other things. But just this one aspect has gotten very complicated, because whereas a 2-year-old, if you asked them to make a peanut butter jelly sandwich, they would immediately go to the peanut butter, open it, find some bread, some jelly, and be done with it. If it's a computer program, it has to be told everything. It doesn't now, it would remember it if you saved all the statements. But that initial creation of the logic necessary to make a peanut butter sandwich is incredibly detailed and very labor intensive. One of the reasons that there is still a shortage of programmers is because it takes so long to create quality programs. It's labor intensive, and everybody knows that time is money. So most companies are looking for ways to save time, and that will lead to our second topic in this course, which is object-oriented programming, which is very important in code reuse, or developing code that we could use over and over and over again, which again will save us time and therefore money. Flowcharts is another way that programmers model logic, and flowcharts are very visual, whereas obviously pseudocode is very linear. The nice thing about flowcharts is that if you understand what the symbols mean, you can take a non-programmer and typically give them the kinds of information they need to understand the program fairly quickly or easily. Non-programmers have a hard time with pseudocode because it's kind of linear, it's a little bit detailed like a math problem. So the advantages of flowcharts are typically that you can communicate to people who haven't worked with logic before fairly easily. The advantage and the disadvantage, of course, is that when you start working with flowcharts, even a very simple problem based on the number of symbols we have to have and position can take up a lot of space, a lot of diagrams, a lot of paper. They can be very large very quickly. So therefore, they're not terribly efficient. We will only use flowcharts the first couple of assignments. Pseudocode is more like the actual programming statements we're going to write as programmers, and the intent here is to get you ready to be programmers. That is more like programming code. That's an advantage. It's much more compact and easier to document. That's another advantage. A full list of the advantages you can find inside the textbook. This is a side-by-side comparison of a flowchart versus pseudocode. You can see the difference in terms of how much space it takes. You can see that it may be visually easier to follow one versus the other, and we will spend some time, if not this chapter, the next, explaining what some of these symbols mean, because they are very particular in what they can hold. And if you know what they mean, it makes it that much easier. In fact, quite often I'll explain a flowchart is kind of like a picture's worth 1,000 words. That's typically what happens with flowcharts. This is an actual program of the information that we initially had in pseudocode converted to Python. So if I go back a couple slides and look at the pseudocode, you'll see how it's been changed slightly to conform to the rules of syntax and programming for the Python programming language. And they have to be in a certain order for Python to understand it, whereas pseudocode, anything goes. But again, the problem with pseudocode is I can't write it at the computer. Pseudocode is like a blueprint. It's just a visualization, or it's just a description of what I want to do. Kind of like, well, I can have a Google map, or I can have Google directions and text. The map would kind of show me visually what's going on and be very, very accurate. The text might be a little difficult to follow. It might be more interpretation. That would be the difference between pseudocode and a program itself. The program will run, and that code letter will execute in Python. Now, technology is all about systems. Systems, excuse me, take inputs that are processed and convert them to outputs. Systems are subsystems. So, for example, in your car, you have a stereo system, a cooling system, a fuel injection system, the list goes on. All those systems talk to each other, so input from one system could become as the output from another. So, for example, when you're running low on gas, your sensor in your gas tank will send your dashboard, another system, a message saying, please process this signal indicating we're low on gas. Once that signal is processed, a light appears on your dashboard saying that get some gas. Also associated with this systems or systems methodology is SDLC, System Development Life Cycle. The best way to describe this is there's two ways to solve any kind of problem. There's a rifle approach and there's a shotgun approach. The rifle approach is very carefully planned out, aim is taken, one shot, it's done. A shotgun has got a big spray pattern and it's just guessing until you get it right. An example might be this. If I wake up in the morning, my car doesn't start. Well, I know the car needs to run by an engine. I guess I better replace the engine. No, I don't think that's probably the answer. Whereas a rifle approach might be, okay, does the battery have juice in it? Is it charged? Are the cables connected? Does the car have gas? All of which would take less time and money and be a much more systematic way of solving a problem. This is what's happening with SDLC. Now, this particular slide, you'll find all this stuff in the textbook, reflects the programming development life cycle. And we have some other slides here. They all kind of follow more or less the same order. Okay, it'll start with a, let me go back one more, with a planning phase, and this is, they also call this a waterfall approach, where what I'm going to do is I'm going to look at this problem and try to understand, is it an opportunity, well, this item, understand if it's a problem or an opportunity. The next thing is I'm going to gather information that's going to help me better understand what's happening. I'm going to ask the people involved. I'm going to look at some data. I'm going to look at some reports. I'm then going to design a decision. The design could have a couple different phases. It could have a conceptual design, which is what the other slide shows us, where I'm going to model the application. And then also has a detailed design where I'm actually going to create the programming code. This is typical of a programming SDLC. I'm next going to develop the code, test the code, put it on the system, let the user use it, train the user how to use it, create some documentation. And then there periodically will be times I need to change it, update it, fix problems, etc. This is called a waterfall approach. It's iterative. It just goes round and round and round for the entire life cycle of the program. It's phased. It's considered a very logical. I think you could probably compare this much like the scientific method in a science class too. Programming. This is not a programming class, but we're going to talk a lot about programming. We're going to talk about syntax. We're going to talk about executing a program. We're going to talk about compiled versus interpreted programs. Python is a compiled or is interpreted program, which means that its statements are executed a line at a time, and each line is tested by the interpreter to make sure it's correct. A compile language is the .coms, .exes, or .exes or .dlls, which are compiled into binary machine code for that language. They tend to be faster programs. Okay, for example, the Windows operating system is a compiled programming language, whereas the interpreter tends to be a little slower, but probably a little easier to put together also. Fewer rules, for example. We'll talk about both of those. The actual phases involved with getting a program or putting a program out there are underlined in this particular diagram. I'll let you guys read this and let me have any questions. And the only other type of program that we can run into today, this is something that's fairly new, is a runtime or virtual runtime machine program. This is what Java and .NET runs on. And basically what happens here is there's a program that has to be present on the operating system. And what happens is when let's say a .NET or even a Java, when a Java class file is executed, it looks for this program to be installed in the operating system, and then it goes through that program, which then converts those source code statements or P code statements in the case of Java into machine language statements, which are then executed by the computer. This compiler tends to write the smallest, fastest code. Interpreter tends to be very flexible. Most of the web stuff is the internet web applications are interpreted programs. And then runtime is very useful when you want to write it once and run it on many environments. So for example, if you want to write a program that ran the same on Apple and Windows, both environments, both platforms, you would probably choose a virtual runtime solution like Java, and that would do it for you. These terms here end up showing up in your true false multiple choices. Take some time in these guys, look them over, okay? Some of them will show up in the assignments, some of them might even show up in a discussion question, but not so much for discussion questions now. This is going to be your first chapter, and look over the rest of the chapter in the textbook. Any associated assignments with it, there is an assignment for chapter 1. And of course, always let me know if you have any questions. Thank you.